Good afternoon, everyone. So welcome to our session. So my name is Kai Liu. This is my teammate Lu. So we are both from Yahoo ads and data team. So today Lu and I will be talking about Yahoo's user profile platform and its evolution. So basically, actually this platform includes three parts: the data, user modeling, and profile serving. But today we will be mainly focused on the data part. So, okay, so here is today's agenda. So I will take care of the first two parts, and Lou will talk about the schema design and the optimization work we have done so far. And lastly, we will briefly describe other areas where we will be looking at in the future. Okay. So what is user profile? So because in different contexts, user profile can mean totally different things. So firstly, we want to set the context, what we are talking about when we say user profile in this talk. Okay, so what it refers to when we say user profile, we captured a definition from Wikipedia. So user profile is kind of a visual display of personal data associated with each specific user. So in other words, user profile is a digital representation of a person's identity. So that's how we are defining the user profile in this talk. So one way we can profiling a user is to attach different tags to a person so that computers can handle it. So here's how Elon Musk's user profile looks like. So this man is 40 years old. Obviously, he's a male and born in South Africa. And he's the brain behind a lot of big names like SpaceX, Tesla, Hyperloop, SolarCity, OpenAI, just name a few. So this is just to give you guys a sense so how the user profile looks like for an individual person. Okay, so unfortunately, Elon Musk, he's a public figure, right? So you can simply get his information from like a Wikipedia or any other news website. But how about thousands of millions of other people out there in the internet? Because you cannot easily get the user's interest, the user's demographic data that easily, right? So how can we do that? And as you know, many internet companies like Facebook, Google, including Yahoo, they are making money mostly from their advertising business, right? And a big portion of advertising is about user understanding. So if you can understand your user better, then you can deliver the most relevant ads to them. Then you can make more money. So in user profile platform, we collect the user data from different data sources and build a profile for each single user. And it can serve different use cases. The most important use case at Yahoo is the ad serving. Because the ad serving system needs to be able to retrieve a profile for any given user, as long as we know it, during the ad selection. Then make sure we deliver the best ad to the user. So that's the first use case. The second one, our user modeling team. They need to read all the user data and then try to leverage complicated user modeling, machine learning model to tag the user with their interest so that we can predict the future behavior of the users. And then lastly, the audience insight. So audience insight is basically about providing advertisers the access to the audience interest and the behaviors. It's more like a visualization view on top of the users for them to optimize their campaign. Okay, so logically, this is how user profile looks like. So Lou will be talking about the physical implementation, how we are designing the HBase table to store the data. But logically, user profile is you can think about it more like a large key value store, where the key is the user ID. The value is actually the aggregated user data in past several days, 30 days, 1 year, depends on the data type. So as you can see, we are collecting the data from user activities because Yahoo is a website. So we can collect the user activities like page views collected from the web server and search queries from the search engine logs. And we can also get a lot of activities like add interaction, add view, add click from the ad servers. So those are the user activities. So we are collecting activities as an event. The event is something like who did what at what time. That's an event. That's user behavior. But the user behavior does not explicitly express the user interest. So we have to extract the representative features from the raw data, raw events. And then our user modeling team, they will run the machine learning algorithm on top of the features and then try to tag the user with their interest. So it's like a feedback loop. We aggregate the user data for each given user and then provide an interface to our user modeling team. And they will run the machine learning model and then feedback the scoring result to our user platform. So on the other side, we have another category called properties. So the difference between properties and events features is that properties tend to be like a static information, like your age, gender, and the devices you have. So in most of the cases, when you register as a Yahoo user, you will tell us your year of birth, your age, something like that, right? So those are the properties. On the other side, we can also extract some information from user activities. For example, associated with your page view, your ad interaction, we can get some user agent information. And from user agent, we know from which device you are interacting with our website, right? Like you are using iPhone to access Yahoo, you are using a browser to access Yahoo. So we can understand how many devices you have, right? So those information are also pretty important from the targeting perspective and the advertising perspective. Okay. Okay, so like I mentioned earlier, so the way how Yahoo identifies a user is using the user ID. So we have different types of user ID at Yahoo. So I categorize them into two categories. So the first category is desktop users. And then for all the desktop users, if you are a registered Yahoo user and you are logged in past 30 days, then we can identify you as using a certain way, which is derived from your registered user account. So we call it YUID. It's Yahoo user ID. But for the from the user policy point of view, right? So we cannot use the Yahoo registered user ID directly. So we applied a one-way hash based on Yahoo user ID to generate this something called SID. So this is a completely anonymous user ID to identify a registered user. And for the non-registered user, so we will use the browser ID to identify you. So browser ID is basically the first 13 characters from your B cookie, your browser cookie. So that's for desktop. So for devices, right now we are mainly focusing on the two types of devices. One is the iOS. We are using the IDFA. That's kind of an industry standard. It's an identifier for advertisers defined by Apple. And another one, they call it GPS AID, which is Google Play Service Advertising ID, which is for the Android devices. So we are using those IDs to identify the users behind the mobile devices. Okay, so to understand this is important because Lou will be talking about one challenge we have in this project, which is a data skew problem, right? So this has something to do with the user ID type. Okay, so the second actions, I will be talking about the architecture evolution. So how the old architecture looks like 1 year ago, and what's the problem with the old one, and then how we solve the problem in the new architecture. Okay, so this is a traditional or classic architecture for most of the data system on top of Hadoop. So basically, you can collect different data from different data sources. Especially today, the IoT, you can generate different signals. So we need to have a data preparation phase before we do the calculation. So the data preparation is more like an ETL job. So you can write pig, hive, or native MapReduce job to process the data, clean the data, and do the transformation. Sometimes you will do the projection because you don't need everything from the raw data. So that's the first phase. So once the data is clean and the format is friendly for your computation job, then you will run your MapReduce job on top of your intermediate data. And then you will, most likely you will output your data back to HDFS as a deep storage. So this is how the old architecture looks like at a high level. So we have an ETL job running every day, trying to collect the data from different data sources. But the frequency for our upstream data can be all the way from 5 minutes to 1 week. But because of the nature of HDFS, we cannot process those data in different frequencies. So we have a daily ETL job to do the data preparation. And then we have an aggregation job, read the previous day's user profile, and then do a big join with the incremental data, and then output it back to HDFS. So in order to support like ad hoc queries, so we put the data in Hive as well, so that people who are familiar with SQL, they can write ad hoc query on top of Hive. So for the ad serving, so they are reading the data from HDFS directly, and then using a key value store technology to serve it on runtime. So instead of sending the full data to ad serving, we generate an incremental user profile every day for the ad serving system. So that's how the old architecture looks like. Okay, so what's the problem with the old one? Actually, the old architecture served us pretty well in last 1 year. But when we are getting more and more data in the user profile platform, we are seeing some issue. The first issue is actually the most obvious issue, is that the aggregation is very expensive. Because every day we only saw like 30% of the users get updates. But in order to do an update for the user profiles, we have to load everything from HDFS, because you cannot do the random write on top of HDFS. So you simply read everything, and then join with the incremental data, and then output it back. So it's very I/O expensive. So that's the first problem. Another problem is that our input data, they have different frequencies. Some data is even in event streaming fashion, right? But we cannot run multiple jobs on top of HDFS, like what I mentioned earlier, right? You cannot do the in-place updates for the data. So we can only use one single frequency to process data with different update frequency. And the last one is that lack of the capability to process event data, event stream data. That's also a downside of the old architecture. Okay, so here are the main components we are using in the new architecture. We are using Spark because it's fast in many ways, and it's also providing a consistent tech stack to cover both batch and streaming data. The second one is actually the core idea for the new architecture. We are using HBase instead of HDFS to store our user profile. Because we can do the random read-write with HBase, we don't need to load everything into our computation job to do the big join. And then lastly, but not least, we are still using Hive as a query interface. So I will be talking about our future plan to explore another interactive query engine for our user profile. Okay, so this one is pretty simple. The idea is we're going to use Hive to store the data. We're going to use Spark to process both batch data as well as streaming data. And then the second part is the same. So we still need to support user modeling, support audience insight, support ad serving. But the turnaround time is much shorter than the previous architecture. So right now we are able to, the SLA for the hourly feed is 1.5 hours, but previous everything is like more than 1 day, 30 hours or so. So that's the big win with the new architecture. Okay, how problem got resolved? So incremental update to avoid the full load. So HBase will only be accessed when there is an update for the user. If there's no update for the user, we won't read any data for that user. And multiple Spark jobs running concurrently. So job frequency is really determined in accordance to how soon its input data becomes available. So if the input data becomes available every 1 hour, we're going to run an hourly Spark job to ingest this data to the user profile. If the data is available every 1 day, then we have another Spark job running every day to process the data. So Spark streaming is kind of fills the gap of lack of capability to process event data so that we can ingest the event data much faster than the previous architecture. Okay, so I think that's pretty much my side. Lou will talk about the...
Hi, everyone. I'm Lou. So here I'm going to talk about more details about the implementation. So first, I'm going to talk about the schema design part. So to find out the suitable schema for the user profile, first we have to understand our data very well. So as Kai mentioned in previous slides, so user profile can be divided into 4 parts: the property, the events, the segments, and the features. So first part is the properties. So properties is a set of attributes such as age, gender, and other demographic information. So the data type is basically key value pairs. And the update pattern is override only, means the new value will override the existing values. And the properties will be used in 3 user cases: ad serving, user modeling, and audience insights. The second one is the events data. So events data are time series data. For example, the ad click history or page view history of a user. And the update pattern is append only. And events data will be used to create audience insights. So the third one is segments. So basically, a segment is a tag we created to represent a kind of interest. For example, football fans could be one segment. And a user segments list is very useful in ad serving and audience insights. So it's the list of key value pairs. And the update pattern is read, modify, write based on our user case, which means you have to read it first and do the modification and write it back to HBase. The last one is the features. So features are the data that are some derivative features come from the events data. So the update pattern is a combination of both override and read, modify, write. And the features data will be used in ad serving and user modeling. So before we get into the schema design, so here's a brief introduction of HBase data modeling. So in HBase, tables are made of rows and columns. So columns are grouped into different column families, and you can dynamically add column on the fly. So the intersection of rows and columns are cells. That's where the actual data is stored into. And the data type is byte array, which means you have to take care of the serialization and deserialization of your application layer. Each row is associated with a row key. And all rows are sorted by row key. And the data access is also by row key. Here's an example to help you better understand that. So this is the user's properties table. Let's first take a look at the key part. So here the key consists of the prefix ID type and the suffix user ID. So because HBase rows are sorted by row key, and the users with common ID type in this design will be close by, and it can satisfy query like get all users by the given ID type. Also, you can also sampling the users based on ID type, because all the users of a given ID type, they are close by. So we have different columns, age, gender, and device informations under column family properties. And here we use a very nice HBase feature called versioning. Versioning allows you to store the last several versions of the data. So here we store the last 3 versions of the column. And in this way, you can easily roll back if your data get polluted. Here comes the events table. So in the events table, the key is a combination of ID type, user ID, event type, and timestamp. And the rows are sorted by timestamp, which means you can easily do a range query by timestamp. And here the value is serialized event byte array here. Then it's the segments table. The key design is similar with the properties table. And here we have multiple columns to represent a segment that coming from a specific source. So we have multiple groups starting user profile in Yahoo and come out with the segments. And here we separate the segments list based on the source. In this way, they can update each other. They can update the segments independently. We don't need to take care of the concurrency control. So because we have different user cases on different part of the user profile, and then we come out with different access patterns. So here is a comparison of the properties table and the events table. So the support query type is different. For properties table, that's more like a single data point access. For example, get age, gender of this user. And for events table, that's a range query by timestamp. It's like a get events of this user from May 21st to May 22nd. And the write pattern is also different. So in properties table, we do write only, and then we keep multiple versions to take care of the data pollution. And in events table, we do append only, and we use another HBase feature called the time to leave to let HBase to auto-remove the expired records. So as I said, the rollback strategy is different. So for properties table, you can set this time range in your query to fetch the last version in the application layer if your data gets polluted. And in the events table, you can filter out bad records in application layer, and you can do deletion based on timestamp if necessary. So then comes to the optimization part. So to better scale our application, we do several optimization checks. The first one is very traditional but very useful to pre-split the tables. So in HBase, when a table is first created, HBase by default will only allocate one region to your table. That means all your requests will come to one region server initially, no matter how many servers you have in this HBase cluster. And HBase does it when your region gets larger, it will split into 2 regions and so on and so forth, and how the table grows. And HBase does it in this way because it doesn't know your data distribution from the beginning. But if you can provide that to HBase, you can avoid such a cold start problem. So here's an example. So in our user case, we can easily get the data distribution of different tables. For example, here's the data distribution of the properties tables. As you see, we have more than 50% of data are with bcookie ID. And then, according to this data distribution, we can come out with the pre-split strategy to allocate more storage resources to the user ID with the most users. The second one is also very important. We do pre-aggregation events in Spark. So a simple fact. So we have 1 billion native edge events per day on 100 million users. So if every one of them transformed to one write to HBase, that's going to be 1 billion writes to HBase. So first, this solution won't scale if your data grows. Second, so from our user case, actually, we don't need to support single event access. So then this brings us to the solution that actually we can group all the data by user ID and a fixed time interval based on the event type. For example, the time interval could be 5 minutes, half an hour, or even 1 hour. In this way, we can dramatically reduce the number of writes to HBase. So here's a histogram showing that the number of records before aggregation and after aggregation. You can see we can reduce the writes by 10 times here. So similarly, we do pre-aggregation for the updates of feature table as well. So we have 5 billion app activities per day on 500 million devices. And we also have 1 billion search keywords per day on 60 million devices. So we can combine them all and aggregate them on user ID. And then we do write to HBase, do writes to HBase. This can reduce the number of writes and reduce the overhead. So the third one I'm going to talk about is we do lazy aggregation for inactive users. So the main goal here is to reduce number of read modify writes to HBase. So sometimes, so in our user case, we have to support read modify write, and read modify write is expensive because every request is 1 read and 1 write to HBase. Actually, HBase support is the best use case for HBase is a write-heavy load. So if the read load is almost the same with write load, then that's not the best use case for HBase. And then even though we have to support it, we can still find out some ways to optimize it. So then we take a second look at the table, and we find out following 2 facts. The first one is a large portion of the user might not be accessed frequently. So during ad serving, we have to provide the user profile, and not every user frequently be requested. Second one is we have multiple jobs that update to the HBase, and update jobs are not evenly distributed over time. Means sometimes within some time interval within the day, we have several jobs being triggered and updating, and sometimes none of them, and the load is very low. So then actually we can do lazy aggregation for inactive users. So what does it mean? So first, we maintain a set of users as active users, based on the event history and ID type. And then we do read, modify, write for active users only during the Spark job. And for inactive users, we only append the updates for them. And then we will have a separate batch job being triggered that merging the updates for the inactive users. And if the request coming before the separate batch job being triggered, we will do this merging upon request. And this can dramatically reduce the number of read, modify, writes and to better scale the application. So the last part is the optimization for Hive. So because we support user modeling and audience insights in Hive, so we need to sync data between HBase and Hive. So here we use HBase feature called snapshots. That so we can take snapshots periodically and transfer the snapshots to the Hive. And then Hive access data using a feature called HBase storage handler. So in this way, we can bypass the HBase API to transfer the data between HBase to Hive. OK, so the last part is the future works. So first one is we want to explore Impala and Presto for better query performance. So right now, we use Hive to support ad hoc queries. And we want to try this two very popular system to support queries. And second one is we want to support API for incremental modeling capability. So sometimes, so right now, most of our user modeling machine learning algorithms are in batch mode. And we want to expose as an API from HBase that we can do incremental modeling on HBase rather than everything from Hive. So that's it. So actually, we.
OK. So basically, right now, this project is still like under the experimentation. So we did talk to the Yahoo Hive team. So they're running Hive on top of a Taze, but we want to expose both options. Because I don't know how fast Hive on Taze can be, but we do have a use case one to support the interactive query, which is like in several seconds, something like that.
So you mentioned, for instance, on the event table, you serialized the event and then stuck it on the table. Were you doing any kind of like normalization to that event, or just sticking all the data about the event right on the table?
All the table, but all the data, but with some aggregation.
Okay.
Yeah.
So since you are supporting HBase and Hive later, so
Right.
have you considered having a Hive table, external Hive table, to expose data in HBase?
Hive table, you mean the reverse direction?
The data is in HBase, right? HBase
Right.
table. Then you can have you can expose that data from the Hive table.
OK, we.
There's a capability.
Yeah, I know that. But so to be honest, we didn't think about that way because right now we are using the reason for using HBase is that we can do the fast aggregation without do the full load, right? But if the data is in Hive, so right now we have to let Spark job to read data from Hive and then write it back to HBase. So.
Yeah, and also we support as serving from HBase to.
Yeah. OK. Please.
My question is, how do you mitigate the major comparisons across a big? I mean, you have a very big HBase cluster. So
Right.
how do you mitigate the
Okay.
Okay, so the question is how often we do how we do major compaction on HBase. So so our HBase cluster is maintained by the HBase service team. So I don't know the exactly details, but as far as I know, so we have a script to periodically check the load and do the compaction on its own. At any given time, there will be only a few region servers doing compaction, just making sure the overall service will not be impacted.
Do you have transactional use cases for region event data?
No, we don't have. Yeah, the question is that do we have use case to do the transactional events ingestion, right? Yeah, no, we don't have.
What reads?
Sorry?
How about reads?
Read. So right now, like what we mentioned early. So events data is more like we use events data as a raw data, right? And then we extract the representative features from the events, right? Then the user modeling is running on top of features only, not events. So events data is more like for the audience insight. For audience insight, they basically do the full scan, just read all of the events, but only extract some information, like the devices behind the events, right? And something like the user agent, which browser you are using, so that they can generate some insight, like some 80% of the users, they're using Chrome, 10% of the users, they're only using like Firefox, right? Those are the use case for events.
Look at your table schema. For Loki, you have a user ID type in front of it. Are there any cases that you need to scan across multiple user ID types?
Yes, but very rare because from the user modeling point of view, so they have different models for different ID type. So anytime they only run their model on top of one particular ID type. So because the model can be totally different for devices and for the anonymous users on desktop.
Right, but when you do that, how you do that? Do the parallel scanning? How do you do that?
Yeah, they are doing the parallel scanning.
I mean, how do you do the parallel scanning? I mean, HBase doesn't come with the built-in feature for parallel scanning. I have to.
Oh, okay. I see what you mean. So that's why we have a Hive interface, because most of the time the user modeling is doing the full scan. HBase is not designed for the sequential read, right? It's better for the random access. So basically, they can tolerate the latency. I mean, so we can make the data available in HBase in 10 minutes or so, right? But from the user modeling point of view, they can tolerate the additional latency, so that we are loading the data from HBase to Hive, then they will do the full scan on top of Hive instead of HBase. Yeah. Oh, yes.
Same user may use different device or use different application to access your system. So basically, you end up with different ID. You guys have some way to connect those different ID and identify, oh, this is the same user.
Oh, okay. That's a good question. So that's like the question was that are we collecting or merging different user IDs for the real person, right? Yeah, for the same user. So basically, that's another topic which is called a cross-device identity, right? So basically, you can access our website from browser. You can access website from your iPhone, right? But essentially, you are the same person, right? So that's a good question. So in the current design, so you will end up with multiple profiles. One identified with your browser ID, another identified with your IDFA. Let's say you are using iPhone, right? But outside of the user profile, we have another like a mapping table, which is grouping BID, IDFA with another ID. We call it class ID. It's like a kind of a class grouping problem, right? We can grouping different IDs for the same user together. And then for the guys, for the system, they only care about the real people. They don't care about you have multiple user IDs, right? They will look at that table, then merge different user profiles for the same user together.
How do you know they're same user?
Okay. So that's kind of out of the scope. But I can tell you one thing. The one case is that we are using the household IP, right? For example, if you are Okay, that's not a good example. Okay, I guess we can talk offline. So this is not our expert. Go ahead.
The first question is, do you transfer all the data from HBase to Hive? And the second question is like, from the Hive's perspective of view, like the freshness of data is decided by the frequency of, like you transfer the data from HBase to Hive. Like how do you decide the frequency of it?
Sorry, what's your first question?
The first question is like, do you transfer all the data from HBase to Hive or some of
Okay, let me answer the first question first. How we are transferring? Are we transferring all the data from HBase to Hive, right? Okay, so right now, yes. The short answer is yes. We have to transfer all the data to Hive so that the modeling team can use all of the user data. Yeah, that's the answer. So what's your second one?
If you are transferring all the data to it, which means like it should be like a large amount of it, which may have a lot, like large, which may take a long time. So
Right.
my second question is like from the Hive's perspective view, so for the ad hoc query, the freshness of the data should be decided by like how frequently you transfer the data from HBase. Right. So
Right.
how do you decide that frequency?
Right. Maybe Lou, you want to answer this question?
So as I said, so we use a separate API to directly transfer the H files to Hive and using the HBase storage handler to read the file from Hive. So we do this like once per 2 days. And then in this way, because we can tolerate some consistency here, and our user modeling can tolerate some consistency here.
Okay, I think we are running out of time, so maybe we can discuss any more questions. Thank you. Thank you, guys.